So many of you in the audience, and me as well, we think about extending general relativity in order to explain what is the nature of dark matter, dark energy, even hopefully explaining some of the cosmic tensions that we have been hearing about. And usually the way we do it, we introduce a new degree of freedom to our gravity sector, which would be possibly the source of dark matter, dark energy, etc. If you want this new degree of freedom to have a cosmological impact, for instance, to have some impact on structure formation, maybe solve the sigma problem, or effect on the background expansion of the universe, or the H0, etc., this new degree of freedom should be quite light. That means you have a range of gigaparsec scales, megaparsecs. Otherwise, if it is too small, then the effects are very small, and it's less promising to have to be solutions for the problems that we've been talking about here. Now, we all know that we can't just change general relativity without taking into account all the different bounds and constraints that we have from gravity experiments. Those experiments come from a different range of scale, from laboratory experiments on Earth, on the system, binary pulsars, and even the form of the gravitational wave that we see from mergers of black holes. So how do we do that? How do we modify gravity, having a light degree of freedom, which we want it to be strongly coupled to the sum-model fields without screwing up all these bounds? Well, the usual answer for that is that we should have a screening mechanism embedded in our theory of modified gravity. And usually with that, we can safely have a theory of modified gravity, which might be of dark energy candidate, and might also hopefully solve some of your cosmological tensions that we have seen in the data nowadays. Now, the screening mechanism, there are different types of screening mechanisms, but in general, for a general scalar density theory with the general actions, we have a scalar field which might have a non-canonical kinetic term, self-interacting potential, and a couple to standard-model fields. Usually, this kind of extra degree of freedom will induce a Yukawa correction to our Newtonian potential, which can be in a very general way written like this. And of course, when we perform experiments, for instance, tabletop experiments on Earth, like the Etowashi experiment, we don't see these Yukawa corrections. So we have to kill this Yukawa correction with a screening mechanism, a way of hiding this extra degree of freedom. And there are several ways to do it, and we can either play with, for instance, with the mass of this extra degree of freedom to make the environmental dependent, so it becomes very heavy. These fields of very short range in regions of high density, and that would be called, for instance, the chameleon screening mechanism, which, for instance, can be applied to have hard gravity. Or we can also play with the fact that the coupling between this extra degree of freedom and the standard-model fields might also change in the environment. That would be the dilaton or the symmetron screening mechanism. And you have other possibilities, which is played with the non-canonical part of the kinetic term, which, if we play with the first derivatives, we have, for instance, the camouflage, or that usually is applied, for instance, Mont type of theories, the ionic, etc. We can also go for the maybe one of the most popular ones, which is the Weinstein screening mechanism, which is just another way of a very large inertia. So again, the non-canonical term is huge and makes this Yukawa correction to vanish in the regions where we don't see any modifications for gravity. Now, one thing that the screening mechanisms can assure us is that, for instance, when we look at the PPN parameters, the gamma parameter, for instance, we know that from the Cassini experiments, we have a bound which gamma is very close to 1, or order around 10 to the minus 5. So it's really, really close to 1. We know that in GR, the gamma parameter is about 1, and in theories of modified gravity, the gamma parameter will be a function of the volume of the field within the solar system. So, for instance, for the symmetron, there's this form, so it's going to be proportional to phi square and the Newtonian potential, etc. In the model parameters, for other kinds of theories of modified gravity, we'll have a different form. But usually, the gamma parameter becomes a function of the field. And what the screening mechanisms do is that they make sure that the gamma parameter is very close to 1. So this field becomes really small within the solar system, so we don't see it when we perform, for instance, use measurements from the Cassini bound. Now, How do people usually calculate what is the value of my field, my actual degree of freedom in the solar system, to be sure that my theory of modified gravity, which might be the solutions for dark energy and solve some cosmic tension, satisfy the Cassini bound, for instance, okay? And this is what I'm telling you about, what people do in general. So what people do is that you need to know what's the value of the scalar field within the solar system. So what you have to do is basically solve the equation of motion for this degree of freedom. In this case, the degree of freedom is a scalar field, is a time-bound equation for a system like the solar system. So you have to basically solve this equation. Now, the usual approach is that you use the so-called quasi-static approximation. So you assume that the system that you're solving is a virialized system, is in quasi-stationary mode, and that the field that leaves our actual degree of freedom that will live in the solar system basically decouples from the cosmic evolution of the field. So we can neglect time derivatives also, which mean that the spatial derivatives on the field are larger, and what you do is basically solve this equation. Usually people assume a spherical symmetry, etc., and you solve this equation, for instance, for a massive object like the sun, and see what is the profile and the volume of the field in the solar system. And when we do this naively, that's the same also. So you solve for the scalar field, you solve for the Newtonian potential, and you get some profile of these fields in there. Okay? And what you do when you have the profile of the field, you can just, for instance, try to calculate, okay, so if I have the Newtonian potential here, I can calculate the Newtonian force, which will give me an acceleration, for instance, for the planet, for instance. And I also have the scalar field, which has a profile, so it means there's a spatial gradient, which will also affect, for instance, the orbits of the planets. And when you have the profile of the field as well, you can just plug it into your expression for your gamma ppm per meter and check that this number is consistent with the Cassini bound. So that will be the general approach. But in fact, what I'm showing here, that's the profile of the field if this modified gravity has no screening mechanism. The screening mechanism, what we will do is that we'll make the scalar field profile to be much shallower. Okay, so the value of the field usually is much, much smaller than the one from the Newtonian potential, and its profile is much shallower. And there's also even an effect, for those who know, it's a thin shell effect. So the field basically here, very massive objects like the sun, or the earth, etc., is going to be basically constant. And that means that the gradient of the field is going to be very small, which means then that this extra force coming from the scalar field, so-called field force, is going to be always much, much smaller than Newtonian force. So that's one of the consequences when you have your screening mechanism. So people are very happy. Okay, well, I won't see my actual degree of freedom changing the behavior of the orbits of planets or changing the Cassini bound. And for the Cassini bound, what you'll do as well is that you calculate, again, the value of the scalar field here. So it's going to, since it's a value which is much lower than the Newtonian potential, phi squared is going to be very small with respect to Newtonian potential. So you satisfy that the ppm per meter is always much smaller than the phi squared. Okay, so that's usually the usual approach for people who work in modified gravity, where we have a light degree of freedom strongly coupled to some amount of fields, and we say, well, now we can relax, go to the beach, because nothing will happen, you know. My theory of modified gravity is safe, you know, because the screening mechanism is really effective. The problem is that this might be true for some moments and for a given finite period of time. But there might be tsunamis, there might be waves which spoil the shape and the profile of the scalar field. Okay? And the question that I ask, okay, where could be, what kind of phenomena, astrophysical phenomena, cosmological phenomena, could create a wave that will come through, will enter our galaxy, will enter our solar system, and change the profile of this field, and make it, for instance, a much stronger gradient, or change the field so that will violate the Cassini bound. So I'll give you just two examples. One is waves that can be generated when there's a supernova going off. For instance, in the case of the chameleon field. Okay? So in case of the chameleon field, for those who know, who don't know, the chameleon field is a chameleon where there's an effective potential which changes according to the density of the place where it is. For instance, when there's the star, the density is very high, the effective potential is going to be here high up. But when there's the supernova, which goes off, all the material goes away, and the density in a fraction of seconds drops completely to the background density, and that means this effective potential is released, this energy, this wave which is released, and then the chameleon field, when we calculate the profile here, so this is a simulation that we do, so there's the profile of the chameleon field, quite flat near the star, and then goes to a background value. And what we'll see when there's the supernova going off, you start to have ripples in the profile of the field. So this is, for instance, you can imagine like a supernova, a jet of a galaxy, and basically creating these ripples in our chameleon field, which will then propagate all the way to the solar system. So this is one possibility for kind of the chameleon screening mechanism. Another one is, for instance, when we look at the symmetron screening mechanism. The symmetron has kind of an effective potential. This is a phi square in high densities, but when you go to lower densities in the universe, like for instance in voids, and the symmetron has a symmetry breaking, which can take different values, vacuum expectation values. And that means the creation basically of domain walls. These domain walls, when they're stable, again, they have a profile which is very stable, but these domain walls are in fact not stable objects because matter, there are collisions, and themselves, they can merge and create waves. So the collapse of these domain walls will also create waves, which will then again propagate and might enter our solar system. So the question is then, okay, so I have calculated the profile of my scalar field, assuming the quasi-static approximation. Since there's a screening mechanism, this field seems to satisfy all the bounds that we know, at least within the solar system, etc. What is the consequences if one of these waves enters our galaxy and enters in our solar system? And this is what we try to calculate. I'm just going to give you the example for the symmetron, but we did that as well for the chameleon. So what I'm plotting here is the value, well, in log scale, of the ppn parameter. So the dotted red line, that means that's the Cassini bound. So it's about 10 to the minus 5. So we need that our ppn parameter, which is we computed from the profile of the field from the quasi-static approximation, is this blue line. So here is the center of the Milky Way. This is the outskirts of the Milky Way here. And the solar system sits in about 8 kiloparsecs, so around this green line. So we see that our solar system, the ppn parameter is about 10 to the minus 8. So 4 orders of magnitude below the Cassini bound. So that we would, from a modified theory point of view, would be very relaxed and say, well, our theory is really, passes with high flux all the constraints from the Cassini bound, because it's about 10 to the minus 8 there, and the Cassini bound is 10 to the minus 5. So what happens if we have a supernova, for instance, going off, or a domain wall, in this case, breaking down, and you have these waves of this scalar field coming up? These waves will produce these effects. It will come from the edge of the galaxy, they will enter the solar system, and they will pump up the ppn parameter to very high values, to, for instance, in this case, 10 to the minus 2. So that means this model will be ruled out, because we have these waves coming in. So we then did this analysis. So we have from the quasi-static approximation, if you assume that really there are no astrophysical phenomena which could infer with your scalar field profile, what you have is the dotted blue line. So many people in many models that we use, in fact, I used as well. We have that with, for instance, a symmetry model, which has about a range of, for instance, of 1 megaparsec, coupled to some other fields of the same order as gravity, order 1, Planck units. So we would have that fully satisfy the Cassini bound, because it's like in the solar system is about 10 to the minus 8, and the Cassini bound is about 10 to the minus 5. But if there is one of the symmetron domain walls going off, we will have an increase to 6 orders of magnitude, 10 orders of magnitude there. So that would be, in fact, rule out our model. And for the chameleon model, it's pretty much the same. Well, depending on the position of the supernova, of course, but we have similar results. So, conclusion, basically, this is the main plot for the work, is that if we try to see from more realistic simulations in this case, so we are putting the initial amplitude of the waves over this frequency, here in many years, we can see that depending where these domain walls are, we have increases of the ppn parameter up to 4 orders of magnitude. So this will basically break the efficiency of the screening mechanism, and what you think is a viable theory of modified gravity is in fact is not. So one needs to be very careful about that. Okay. Something interesting as well is that since we have these waves, a signature, a smoking gun of the effect of both the screening mechanism and the existence of these waves in the universe would be that the ppn parameter in principle, the ppn parameter would be in principle an oscillating function. So if you could have an experiment which would measure the ppn parameter, we should see every time there's a wave going through the solar system, we should see an increase of the ppn parameter and then coming down again when the field relaxes again to the quasi-static behavior. Because this is in fact something that we saw, is that when the wave passes, the scalar field changes its shape, the scalar field profile changes its shape in the solar system, but then after some time it recovers the quasi-static profile. So that kind of oscillations on the ppm, that would be a smoking gun for this kind of effects. Okay, so I can finish with my summary. So what I try to tell you here is that if you wish to modify general relativity by including a very light new degree of freedom, which is strongly coupled to the standard model fields, the only way to have it and to evade local gravity constraints and astrophysical constraints from strong field usually are by having embedded a screening mechanism in your theory. Just because you have a screening mechanism in your theory, it doesn't mean that your theory is safe or it's still viable, because usually when you do these calculations, people assume the quasi-static approximation to calculate the profiles of the field, for instance, in the solar system, to see if it passes the gravity tests. But in fact, there are several astrophysical phenomena, for instance, supernovae going off, even the merge of black holes, domain walls in the case of the symmetry model, which can create waves which are outside our virialized structure, our Milky Way, and this way can propagate within our solar system and change, for a given amount of time, the volume of, for instance, the ppn parameter, the gamma parameter. And those oscillations would be the smoking gun for these effects. Yeah. Thank you.
I agree completely with you, because several times people is applying the ppn parameterization of GR with two modified gravity, and this is a mistake, because as you have pointed out, when you are changing the theory, you have to change also the weak field, and then accordingly the ppn are changing in the same way. So the ppn, I want to state that I agree with you. The ppn depends on the theory by which you are starting.
Yeah, agree. Yes, yeah. Yeah, you can't apply directly.
Yeah. And then according to this, also the chameleon is changing.
Yeah.
Okay.
Is it possible that you have a background in these waves and you never reach stochastic equilibrium?
Well, I think in the symmetry model, where you have these domain walls everywhere, I would guess you would have a background, a stochastic background of these waves. For the community, if you produce them in supernovae, then I don't think there's enough supernovae, I think, to have a...
But you've got a bunch of things happening in the early universe that would be, or not the earlier universe, where you have lots of explosions, lots of supernovas.
That's true, yeah, it could be. The thing is that the frequency and the amplitude of the waves depends on the position of the supernova. If they are really far away from us, then I think these waves are damped, so we won't be able to see them or detect them or any changes. Yeah, but it's true that in principle there should be a kind of a background of waves for this phenomenon.
Yes, maybe a simple question. So, what's the time scale of these waves, and what kind of observables would they affect?
So the observable would be the ppn So the time scale will be, well, so the answer for that depends on your model parameters, and it depends the position of where the origin of these waves appear. So when you do here, there's mega year time scales, so it's very long, so we can't have, well, we can put up an experiment measuring the ppn and wait a mega year, like 1 million years, and see if we see an effect. Of course, we won't be here. But this depends on where, for instance, your supernova goes off, or where is the position of the domain well with respect to the Milky Way, for instance, with respect to you. So that's the time scale. And your other question was? The observable. That will be the ppn parameter, so that we can see it from the Cassini satellite, where we see the time delay. Yeah, so that's measurable on this post-Newtonian parameter.
Based on what you said, is there any like supernova explosion that can tell us if this is happening or not, or not?
Yeah, I think there was that's something we are looking for. I think there was a supernova explosion in this was Cliff Burgess from, I don't know if you know, like, you told me there was a supernova explosion, I think, in the 17th century, in the 18th century. It was visible from Earth, and there's something. And he said it was within in the Milky Way, and that maybe we could use that data to put some constraints on our model. We haven't done that because I haven't found that information yet. But it needs to be a supernova in our Milky Way. Well, if it is too far away, then these waves are
Okay, I have 2 questions.
Yeah.
Okay, so the first one is related to this one. So if you change the parameters, like the light, how light your extra degree of freedom, can you like shift so you don't pass by Cassini bound? Will you still have interesting physics or not?
I don't understand what you mean by you change the light. Like what?
Does this shape you obtain here, does it depend on the parameters of your modified theory? Like how light is your...
Yes, it would change, absolutely. Yeah. So this will basically put a bound on your model parameters.
Yeah.
So if your scalar field is much heavier, so here, for this particular simulation, I'm showing you a symmetry model which is about 1 megaparsec at the background level. So if you make it a much shorter range, then this change would be much smaller.
Yeah.
So I'm not saying that I'm ruling out modified gravities with the screening mechanism. I just say that constraints are much tighter than one usually believes. Yeah.
And the second one is, do you have any comments about what waves, what tsunami would you get in the Weinstein screening mechanism? Because you mentioned chameleon.
Yeah, the chameleon symmetry, yes. For the Weinstein, I don't know which kind of phenomena would produce a Weinstein wave. Of course, they also depend on the environmental density, but I don't know. I don't know that.
Could it be like maybe some massive object entering the galaxy or something like extreme, like?
It depends on the density profile. The Weinstein.
No, Weinstein is not density.
Yeah, but it seems that it is depending on, and then it can change. Actually.
Yes, but I don't know how to create the wave on the field, because the Weinstein is a bit different kind of screening. Yes, that's a Weinstein radius.
Okay,
I don't know. I don't know that.
Thank you very much.
2 more quick questions. Sorry, Mars and Mars.
Okay, just a more general question. As you know, in the modified theories of gravity, these extra degrees of freedom can be described as scalar fields or can be described as part of the gravity. So my question is, I would consider these waves to be a modified gravitational waves in these kind of theories. So, for instance, if you have an asymmetric supernova, it would change the gravitational wave profile that we see probably Lisa in the near future. So in that case, we will not have a problem. So this is my question: why do you interpret the new information as a scalar field wave and not as a part of the gravitational?
As a polarization of the new polarization, yeah. No, I think they would be. They are related. The supernovae one, I don't think. Yes. Yeah, you're making me thinking on the Jordan thread now. Yeah. My intuition is much very low on the job constraint there. They are related somehow, but I don't know from the top of my head the stuff.
Yeah, so we are expecting that they move. That was the argument of the majority of the search community in terms of limits are what happened in the past.
That's a very good point, yeah, and I think so, yeah, and so we did that, and I should have mentioned that. So usually for people who work with the chameleons and symmetry models, usually we say that the viable model, it's a model where the range of the extra degree of freedom is about megaparsec kind of scale at the background level. So these bounds from with this that we did, we have to go down to kiloparsec scale at the background level. So the field must be very, very short range. If you keep the coupling to the sum model fields the same, yeah. So you go down to 3 orders of magnitude there. So it's a strong constraint on the parameters. Yeah.